Grazie per essere qui con noi anche nella sessione pomeridiana di JTF.
Thank you very much for being with us in the JTF afternoon session. My name is Friso. I will be the moderator. We'll continue with the presentations of 3D technologies. We have a professor from Thailand, Boonrat Lohwongwatana, who will speak about titanium and precious metal jewelry using the 3D printing technology. He got a PhD in material research at the California Institute of Technology, and at present he is the director of the Research Center of Biomedical Engineering at the Chulalongkorn University. He is the author of many scientific works on biomedical engineering. He has been one of the speakers of the Santa Fe Symposium, his first time at the JTF. He will speak about the different aspects to be considered to be successful with 3D printing, choice of raw material, printing process, shape of the object, and other metallurgy principles which come from the background of metallurgy. Welcome, Professor. You have the floor.
Hello, good afternoon and greetings from Thailand. Sawadee krap. My name is Boonrat, and thank you for kind introduction. I heard some keywords. I apologize that this presentation is in English language. And I'm really thankful to the organizing committee of JTF. Today I'll be talking about titanium and precious metal jewelry using 3D printing. I'm affiliated at the Chulalongkorn University at the Faculty of Engineering, but I'm also talking on behalf of my spin-off company, Metically, which the majority of the knowledge has been derived from. So quickly about myself, I have been working on material science, and these are some of the work that are related to jewelry manufacturing. For example, in 2007, we worked on a project of 850 platinum alloy that could be processed like plastics. And below are the pellets that were formed and thermoformed at only 270 degrees Celsius. Or in 2016, we did the characterization of gypsum bonded investment materials. And the goal is to do the cycle for burnout within 2 hours. So this is the knowledge that we have to obtain through materials characterization before the program for burnout is accomplished. And as I mentioned, Metically is a company that does 3D printing titanium and polymers. And owing to some of the knowledge that we obtained from this company, I'm sharing with you some of the results and the findings that we have accomplished at the company. And since the product is US FDA approved for the cranioplasty, the skull plate, the geometry, the reliability and reproducibility of 3D printing of titanium is actually very important to accomplish. And these are some of the examples of the products that were 3D printed using titanium. But of course, today we're talking about jewelry and something interesting and nice. So we do printings of other objects as well, like the dragon here. As you see below, the keys are actually within the supports themselves. As you see, it's a typical 3D printed parts, rough surface, but there are some fine details that could be accomplished if the processing parameters are correct. We also make some jewelry pieces, particularly for this event and also for the Santa Fe Symposium later in the year. And some of the rings that are dynamic. These are actually two rings that are interlocked forever, and they're actually movable. All the products on the right-hand side has been polished, and you would see some of the finishing process afterwards. Today, I will be covering about the key considerations during the 3D printing of titanium and other metals via powder bed laser melting. We have 3 machines, and we run several materials in our company and in the laboratory at the university. First is the fundamentals. I think this is quite important, but we will conclude them into shorter terms. But the thermodynamics, chemical fluids, and material science are some of the key considerations. For example, the image shown on the left, you would see that the laser comes down. There is a heat source that normally is laser or electron beam. And then you would have several elements down here. The laser comes down, melt, and there's possibility of vaporization and also the melt pool that is down here. So in order to accomplish the right parameters, we usually work on 2 extreme ends of the conditions. First is the borderline conditions. This refers to the conditions that are barely melting the powder at the edge of the heat affected zone. For example, here is this the work on our tantalum. We use only 100 watts laser power and really fast scanning speed of 500 millimeters per second. You would see that there are some unmelted powder here. The other extreme ends is the infill conditions. We use a lot higher power, 250 watts of the laser power at the scanning speed of only 10 millimeters per second. So you would see that with the slow scanning speed and a lot of power, we actually create some pores. And these are actually evidenced by actual experiment and confirmed by the work of the simulations here. This is our collaboration with Professor Shinjo, Professor Pan Visawat, and Professor Roger Reed in the UK and in Japan. The equations, the governing equations, we take into account the viscous terms, gravitations, and interfacial phenomena such as surface tension, Marangoni's flow. If you like wine, you'll see a lot of this in your glasses as well, and the recoil pressure. And then there is a discussion of the laser heat source and the heat loss due to vaporization, conduction, convection, and radiation. The audience is referred to the following publications by our research groups. Now, back to the printing of the objects. We actually have to print a lot of these because, first of all, we want to achieve the similar strength as the rod products or the investment cast products. And there are also concerns about residual stress management. This is a very big problem in additive manufacturing because of the rapid heating and the subsequent cooling of the solid forms. In our work, we were able to accomplish the as-built strength beyond the standards, and also even with annealing and with the microstructure treatments, we could actually still be above the standards for our printed parts. And this is how we do it. We link the knowledge of phase diagrams, phase transformations, physical metallurgy here on the left-hand side. Above, we are looking at the atoms. As we move from nanoscale to microscales, we have precipitates, textures, and then phases. And eventually we have some cracks and surface roughness. And these are all well explained by many theories in physical metallurgy. The photos on the right-hand side, these are some of the microstructures that have been tailored with the subsequent heat treatment profile to reduce the residual stress and also to change the phases of our titanium, of our silver and copper, of our gold, of our tantalum, for example. Of course, the residual stress, we actually have a lot more failures than success when we started off this project. you would see that each of the cubics here were laser melted at different processing parameters. And you would see that some of these would fracture right in half due to retro stress. So here's a fun question for the audience. This is a question regarding the CTE, coefficient of thermal expansion. We have two cylinders here, left and right. And the left-hand side, the inner diameter is a lot larger. It looks like a shell cylinder. And the right-hand side, it's much smaller diameter. Well, the question is, when we heat up this cylinder, the expansion happens, but would the inside diameters expand or shrink? On the left-hand side, it's actually quite obvious that as the cylinder is heated up, the D1 value, the diameter would expand because the material expands right around here. But for D2, there are two things at play here. The outer circle would definitely expand, but the inner circle, the expansion itself could be towards D2. So this is a sort of the fun experiments that we have to do in order to be able to manage the thermal expansion and the residual stress. So I'd like to share with you some of the test parts that we have for several print parameters. We test print the cylinder or shape like this, and also some bone shapes. If we inspect closely, there are 5 different holes here, cylindrical holes, and also just a vertical slabs here. And the vertical slabs are actually very difficult to accomplish, to have 99.5% density or more. So we do a lot of measurements on the inside and on the outside. After the printing, we actually see that there are a lot of shrinkages and there are some changes in geometry. And I'd like to share with you, this is one really powerful sample to use. And I'll be happy to share the geometry of this, the drawing of this piece after the talk. The geometrical change, we also use laser interferometer to check the change in the height and the curvatures. And as you see here, the scans were performed on the head of this is the elbow joint. We perform on the head of the elbow joint and also on the stem side. So you could see that there is a little bit of variation on the stem side and here in the order of tens of microns that we still have to fix. So these are the main 3 processing parameters that any company should be careful, should be worrying about. First is the incoming raw materials. In this talk, I have actually mentioned about 2 types of powder. First is the elemental powder. This is the powder that has been mixed between at least 2, 3, 4, or 5 elements. You could actually mix them and do the 3D printing right away. But this is quite challenging, but it saves the time if you don't want to make the powder. Another technique is to pre-alloy. This is actually becoming a lot more economical at the moment. There are quite a few lab-scaled or small batch production atomizer. The machines that are available, I think some are also at the fair today. You could do the pre-alloy as well in different quantities. The mix, time, motion, and agitation. And we also look at how flowing the powders are, argon atmosphere, vacuum, or open atmosphere. The SLM printing itself, there are quite a few other parameters that have not been mentioned. For example, the print scan strategy. Scan refers to how you move the lasers around. And then there is the other technique like skin core, skin remelt and core. These are some of the techniques that we employ in different shapes and forms of the parts that we make. The blades refers to the blades that move and lever the powder from left to right. There are several types of blades, rubber, stainless steel, and many other kinds. And the supports, actually, there are 3 main usage of the supports. First is actually for the heat transfer. We use a lot of supports for the thick parts, and also the supports, even though we could use a lot, we actually prefer to use little because of the ease of removal and post-processing. So number one and number two are actually fighting each other. If we want really high quality print, we have to spend a lot more time printing, and that's also cost, and also the problem subsequent of removal process that would take longer time. And of course, the last one is the residual stress and accuracy, and this is the combination of both. The post-processing, we do heat treatments in the range of 700 to 1100 degrees Celsius with covering gas like argon atmosphere. We do also the effect of remelting parameters in the laser itself during the 3D printing. And this could accomplish several mechanical properties of the materials, for example, ductile titanium. And we could also show this result by tensile test. We do a lot of microstructural analysis, and this is also serve as a way to understand which post-processing technique is best for our samples. So the basic printing parameters you would see here, so that we understand the same terminologies here. The laser beam comes down. P is usually referred as power, and sometimes we call it in watts. It's the joules per time or joules per second, that is watts. And then there's a lens, and the lens that comes down here, it's kind of focal points here. And then there is the focal offset distance. This is how, the effective length for the laser to come down and melt properly. The scan velocity is the movement of the laser. And here we have the powder bed temperature as well. As we build more and more piece, as we build up the height in Z level, the powder bed actually becomes heated more and more. Here we also have hatch spacing. That's the distance between each of the scan. And then there's a layer thickness. This is the thickness of the powder that has been poured over. And this is the movement of the stage that lowers down. Usually we do this in maybe 25, 40, 50 microns. So all of these, it's the energy consideration here. So we calculate the volume energy density, and it is E, and that's joules per cubic meters. And it's calculated easily as the power divided by the scanning speed, the hatch spacing, and the layer thickness. Actually, this is how you create the volume during the scan. So we do a lot of experiments like this. The layer thickness themselves, the patterns, these show only two patterns here. I will cover the scan strategies later, but we have the island and continuous scan at different speeds. You would see that there are different degrees of porosities here. And we are trying to accomplish at this point a fully dense sample. For the scan strategies, we got this really wonderful review paper by Haoliu Jia et al. And they actually performed several scan strategies. For example, unidirectional scan, contour scan, helix scans. And we actually tried quite a few of them. You would see here on the right-hand side, each of the cubics here were actually scanned using different scan strategies. And with the scan strategies, I think we found the island scans to be working quite well, and also double pass of the laser beam as well. This is also helps in the sense of the residual stress. But as you see, when the energy is too high, there are some holes, there's some pores, and when energy is low enough, there is a more dense sample. But you would see some of these dots down here are unmelted powder actually. So there's always the arts to balance all of these scan strategies to work properly. And here, there are some more examples of the you see here 40 plus 50. These are a double pass of the laser beam, and we found this technique to be working the best actually. So we must conclude though that each different materials and alloys have their own optimum parameters, and they have scan strategies for different applications. For us, the double pass is actually working the best. However, this means double the time for the build platform. So depending on the customers, depending on the implants that we make, depending on the jewelry pieces that we make, we actually alter some of these scan strategies so that the results would be most fitted. Surface finishing, we treat these samples just like jewelry materials. You see the tail of the dragon here. This is the as-built roughness, and we have rough grinding and fine grinding, and also polishing techniques. These are all quite straightforward. Actually, we didn't try anything new except the fact that these are all dry process. Titanium doesn't like water. This could be a lot of interest in some of the audience as well. We do a lot of the surface coloring to the oxide layers, and this is called anodizing. And the color could be selectively filtering specific wavelength with respect to the thickness of the oxide layer. This is a refraction process, but the colors are actually very unique. And some of the colors here, you would see it's ranging from yellow, orange, purple, pretty much the rainbow color all the way to green. And we were able to pinpoint the liquids, the chemicals, and also the time and the thickness of the oxide layer so that we could accomplish a color plates like this. And on the finished products, we could do the treatments and also possibility of making double color or multiple colors on just one simple piece. I'd like to end my presentation here, and thank you very much. I believe your imagination is in your hands, and as engineers, we're just here to do the printing and support you. Thank you very much, and I'd like to acknowledge two subsidiaries of ours, particularly the implant company, and Manufact TI is the 3D printing company, 3D printing as a service. Thank you very much for your time and your kind attention. ขอบคุณครับ Grazie.
Thank you very much, Boonrat, for your presentation.